All right. Hey, everybody. Sorry for the small delay here. I think that we were all waiting on the Wi-Fi there for a minute, but I was also running a little late. So here we go. Please grab this attendance, and we'll get started. So the first homework was due today. Of course, for today's section, I'm not going to go over the homework right now because we're going to go over it with homework 2 as an exam review. But I will make a couple comments on I had a couple questions about one of the problems, and so I wanted to elaborate a little bit to help make sure you're prepared for that, or kind of understand what you can do for that particular plug flow reactor problem. So I'm just going to give you a couple notes on that. Feel free to go back and consider it. You know, as I've told you, the homeworks are graded for completion. So as long as you made an attempt and showed me some work and submit that, we're good in terms of your grade, but perhaps not good in terms of did you learn from it, right? So in addition to coming back to it during the exam review, maybe it's a good idea to go back through it, ask me a question before then and say, hey, you know, what was up with this problem? You're welcome to do that, and I'll do exactly this type of thing. Okay, so looks like the Wi-Fi's out again already, so just take a picture if you need to, or catch this again later. All right. So with that, mostly we're going to be talking about sedimentation and then coagulation. But that quick note, I believe one of your problems has to do with a plug flow reactor, and you're given some information about a half-life, about something being removed, and by some amount of time, half of it's gone. So in that problem, you'll find some sort of indication that you have a half-life, and that's kind of in the context of a plug flow reactor. Now, a plug flow reactor, first of all, we are going to treat as if we have a batch reactor and it's on some conveyor belt that it takes some amount of time to get from the start to the finish, right? So if we think about a plug flow reactor that has some length, we're going to treat some infinitely small little batch reactor there. And I say batch reactor because we did the kinetics with a batch reactor, right? V dc dt equals plus or minus k c to the nth power, right? That was our batch reactor starting point, and we'd say that's in some volume. So when we derived that, we ended up with expressions based on what order it was. So we need to know the order of the reaction. So what does this n equal? And in that particular problem, we know that it should be first order because we're given some indication that it's a per time type of deal, or maybe it tells you in the problem. I haven't taken a look at the problem in a little while. So essentially in that problem, it is a first order, and it's a decay. So that becomes a function that looks something like this. Natural log of c over c naught equals negative kt. So our units of k is in 1 over days or some other unit of time, right? So if you're given a half-life, that's not exactly the k, but we can find the k given the half-life. So a half-life, t at 1/2, we'll say, what this means is c at some time divided by our c at some initial time, and this is the half-life time, we'll say, so t at 1/2, the concentration at the half-life time divided by our initial concentration should literally be 1 over 2, right? And now it doesn't really matter what we started with. That could be 100, and so our concentration is then 50. Whatever the case, this is by definition half-life. So to find k, we can actually use this equation to say, all right, if we take the natural log of 0.5, 1 over 2, say that's going to be equal to negative kt, and you were given some time as the half-life, there you go, you found your K. So then we could say K is equal to negative natural log of 1/2 divided by this half-life time. And you'll see you're given, or you have all the information you need if you know the half-life. Okay, so in that sense, you can find your K that you need for that problem, and then you can finish solving the problem. So if that was a hang-up, or if you didn't do that, go back and double check that that's something that you recognize what you could do for that problem. I think it's problem 7. Okay, so I just wanted to point that out, let you know about that. And another thing to keep in mind is when you solve the final problem, what you're looking for is a time that the water stays in that pipe. So time for the reaction in that particular scenario is going to be the theta, which is V over Q. Volume being some function of the fact that we have a pipe-like system, right? Or maybe legitimately a pipe. So if we have some diameter, then we could get some volume. And you could solve your problem. Okay, does that make sense? Does this help clarify a little bit for some of you? All right, so we'll do a more in-depth, we'll solve each one of these in our homework review. Just had a couple questions about that, so I wanted to make sure that was clear. Okay, so back to sedimentation. Here's where we left off. We derived the mass for particles settling. We said if we want particles to settle faster, we want to increase their diameter, or that it's just a very important feature of how fast a particle will settle. Now, to design a sedimentation basin of some sort, what are we trying to do? Well, we're trying to get a particle to go from somewhere in the water to the bottom, to stick onto the bottom, so that it does not escape and continue on flowing with the water. We just want it to settle out. If you've ever done anything around the area where the Mississippi meets the Gulf, you know there's a lot of sediment. And if you go far enough away from the Mississippi, you will have settled out all the settled particles. And we're going to discuss why that happens today. And if you go way out into the open ocean, the water is much clearer than it is where the Mississippi is meeting it because of that difference in particles in the water. So the Mississippi River Basin and that whole estuary system is essentially can act like, or does act like a massive sedimentation basin. So as we think about the particle settling here, we're going to mostly be talking about engineering design, but it can also consider what's happening in some natural delta systems. So the point is, we need to allow the particle enough time to reach the bottom of a given tank before the water exits that space. We typically design these either as sort of a long rectangle or sometimes as a circular clarifier or sedimentation basin where water is given to the system from the middle. So it's being discharged from the middle and heading outwards to the edge where the water will overtop some rim and you'll collect the water from over the top, giving the water time to expand outwards. And we can actually just take one slice anywhere along this circle and say, okay, here's just one rectangular cross-section that we're going to look at, and that'll be the same no matter which direction you're pointing because it's a circle, right? It's just one radius going across, taking that into 2 dimensions to get the height as well, and then it will look exactly the same as if we took a 2-dimensional slice of one of these guys, again, vertically, just to see how, to watch the particle fall from high to low as it's going across with the flow. So it doesn't really matter if we're looking circular or if we're looking at a rectangular basin. In either case, we're watching that particle. Does it meet the ground before the water exits the other side? So that's pretty handy. The only thing that will change then is the calculation for the area of the basin, which turns out to be important And we'll talk a lot about that in a moment. So let's put some numbers to this and put some a few drawings to it, I suppose. So if this is our diagram where we have flow in this direction, and again, this is a vertical cross section, so we have some height. For the reactor, we'll say this is H. And then if we put a particle in here somewhere, where do we need to put it if we want to try to remove every single particle? At the top on the left, exactly. Exactly right. So if we are considering the most difficult particle to remove, it's the one that's at the top as we're entering the basin. So if we can remove that one by sedimenting downwards with a constant velocity, because we reach terminal velocity with our sedimentation calculations, if that one reaches the bottom, everything reaches the bottom, right? And what you'll notice is we could actually consider some that start lower and have a portion of particles removed, but we'll come back to that. So if this one meets the bottom, and all it has to do is meet the bottom by the time it reaches the exit point. So here's the line that is the line that is our design. For a given class size of particles, you know, some density, some size, for those particles, as long as we meet that criteria, we're okay. As long as we achieve the right sedimentation velocity versus flow rate and area of this basin, as long as all that works out and the particle reaches the bottom and the amount of time that we have, we're good. So the amount of time that we have is our hydraulic residence time, right? That's going to be how long we have until the water leaves. It's a very simple system. We're not well mixed. We're doing laminar flow, so it's just a constant, slow flow to allow it to do that. So these will be, we're always going to design these to avoid any turbulence, to kick the particles around. We just want it to be nice, gentle flow. So that the height of a given particle, if we say that at the top here is the height of the particle that we must remove, we can set that equal to the height of the reactor to say this is our design height. Okay, so this is going to be H equals HP for complete removal, right? So we need to allow the particle to fall a height of H, where H is the height of our reactor. Okay, now I already mentioned the time that we have to fall. We can say this is V over Q, so theta is V over Q. And so what we want to do, and this is the volume here, so uppercase V, what we want to do is understand and connect the settling velocity to the size of the reactor and our flow rate. Okay, so that's kind of our goal, is to design this according to this critical settling velocity that's the settling velocity of the particle. So if we define V naught, so lowercase v naught, as the critical settling velocity, we can say that I'll try to make it a little cursive looking here for you. So the lowercase v naught, we can set equal to Vs for a given particle to say that by design, we are removing this particle. And then that's what we call our critical settling velocity. So V naught set equal to this one, the velocity, the terminal settling velocity of a given particle we're trying to remove. We're calling this our critical or design velocity. Yeah.
So Vs is like a pretty general term, and then V naught would be specific to certain particles.
Almost. But great question. So Vs is what we're going to call the terminal settling velocity for a given particle. Usually we will have calculated this, or we have some particle this is relating to. So this is the terminal settling velocity. This is what we derived last time. So we can say Vs is equal to, this is g times rho of the particle minus rho of the water times diameter of the particle squared over 18 mu. So that was the equation that we looked at and derived for the settling velocity. Yeah, I get the.
Do you assume ideal flow every time?
Yes. So we're always going to be dealing with ideal flow here, nothing weird, nothing turbulent, none of that. Okay, so if Vs is the specific velocity of our particle, we're going to design this reactor to remove that particular particle. We're setting V naught equal to Vs. But this V naught, this critical settling velocity, it can be different, and we then either remove not so many particles or we have extra removal capacity. So if we have a particle that's the size of a bowling ball and the density of a bowling ball, we don't need much room in our reactor to settle that out, right? That's going to settle out pretty quick. So if we design it to remove small particles and then we have to treat bowling balls, no problem. What you'll see is the Vs of the bowling ball is a very large number, and the design velocity for a larger basin is we could remove something that's going a lot slower. So if you get confused at all, remember that what the V naught here we're designing. That's kind of the design criteria for a given reactor. And if we are taking some specific particle that we're trying to remove, then we design it accordingly. Okay, so yeah. It's a good question. Will you design for the smallest particle that you want to remove or can remove? It's a cost question. And what we're going to talk about at the tail end of this lecture is coagulation to improve particle settling, because it does get expensive in terms of how much area you need. So if you want to go really small, and there is a practical limit, diffusion will eventually just keep the particles suspended if they're small enough. So there is a practical limit. You'll never settle some particles. But, okay, if we have some space and we have to treat some flow rate, then how good can we do before we need to just say, all right, let's keep it a little smaller, then let's treat with coagulation and have a second clarifier or second sedimentation basin. So it is a very good question. Usually about the size of silt particles, so tens of micrometers are about the smallest we could do. And even those, usually we might expect to not get all of them, so maybe 20 to 50 micrometer particles would be typical. Okay, so given that we have now this connection between a random particle that we challenge our treatment system with, and we're comparing that to what the treatment system can handle, I want to elaborate on what it can handle. Okay, so that's this V naught. And in order to get there, we can see that we have some height, hp, that the particle needs to travel given some time. And we're just going to go back to the very basics of physics, right? Velocity equals distance over time. And so that means that we could say that our V naught, our design, should be hp divided by our theta. How long does the water stay in that reactor is the time that we have to let it settle. So by design, the design velocity here, the critical settling velocity that we can remove, is equal to the height that the particle has to travel divided by the time that it has to travel. Okay, so it is obviously traveling also to the side with a horizontal vector from the flow rate, but what we're really interested in is it's just making its way downward. Okay, so the velocity to the side doesn't actually impact how quickly it falls. And you'll kind of remember this also from physics. If you ever drop a ball at the same time shooting a ball to the side, they'll hit the ground at the same time. It's different if you're doing paper airplanes because you have lift and all that, right? So But if you took a feather in a vacuum and a bowling ball in a vacuum, they'll both hit the ground at the same time with no air resistance. So this is the deal. We're just looking at the time it takes for that particle to hit the ground and making sure that happens before it exits. So with this equation here, I'm going to elaborate and say, given that we have V over Q as our theta, we can say this is equal to the height of the particle divided by the volume of this basin divided by our flow rate. Now, one thing you might notice is since HP equals H, we could simply write H there. And then we have the height of the reactor. And we will do that because this is our design parameter. So we're going to say this is equal to, and I'm going to do one other thing and say that we'll imagine this is some basin with an area. And again, this could be a circular one. I'm just drawing it as a rectangular for the moment. I'm just going to say this has some area of the basin. We might imagine this is length times width, or pi r squared, okay? If what we're drawing is a radius around some circle. So either the area is length times width, or if circular, pi r squared. All right, so either way, we have an area of the basin. Or basin area. So if we take the volume and put it in terms of the height and the basin area, then we'll see we can simplify a little further. So we're going to say this is going to be equal to the height the particle has to fall divided by the height of the reactor times the area of the basin. That gives us volume divided by the flow rate. So we can write the volume of the basin is equal to the area of the basin times height of the basin, right? So given all that, we can collect these together and say, and then simplify to say that our V naught is going to be equal to Q over AB. So it's the flow rate divided by the area. Now what's interesting here is you'll notice that the height doesn't actually matter. It feels like that's the one thing that should matter because that's how far the particle has to travel, right? So it feels pretty counterintuitive, but it's the flow rate given some area. And again, if you stop and think about it, if I were to pour out my liter of water on a table, and let's say it had a little track or something keeping it on the table. If it's a narrow table, it goes a little fast, right? If I give it a little pipe or something, a narrow channel, it makes its way through that pretty quickly. If it spreads out everywhere, it has more time, right, to travel that distance, that whatever flow rate I was giving it. So as you expand your area for sedimentation, your water slows down. So that means the height that the particles travel, it is actually caught up, like the height that it's going is captured by the flow rate plus the area. It just doesn't look like it is because the height term dropped out. It's a little counterintuitive, but at the end of the day, this equation turns out to be very useful. And this is why, as part of my answer earlier, I was describing that we need a lot of surface area. We need to set aside a lot of land if we're going to sediment small particles, because if you want this to be a bigger number, the settling velocity, or a smaller number, excuse me, you need a larger area of the basin. So if you want to handle particles that are moving slowly, you need either lower flow, that's not usually an option because we have to treat some amount of water, or you need a large basin to let it have that time. Okay, so on this slide we talked about a lot, but it all does come down to pretty simple physics. Okay, And then the other piece of this is we can relate that to our settling velocity for a given particle. All right, any questions so far? Yeah.
Well, this isn't really an important question, but why didn't you just go from Q equals AV? Like the flow equation to that. Why? Because if HP is just equal to H, and it cancels out units, is all of that in the middle necessary?
So why not go straight from here, you're saying?
Why not go straight from Q equals AV and solve for V?
Q equals AB.
Like flow equals velocity times the cross-section.
Oh, AV. Yeah, you could probably look at it in that. Well, let's see. That area that you're talking about, that you're flowing through, would be an area that would be drawn here, and that can be different. As I think maybe it would have to be the same. That's interesting. That's a good question. But what we're talking about is the area of the basin that the particles land on. So it's because that's kind of looking at like a flux type of situation. Q equals the area that it's fluxing through times the velocity it's going. That's not. I'd have to think about it, but that is probably not the area that we're looking at. It's interesting. All right, any other questions? Okay. So I think I just gave myself a little more space to work with here for the same derivation. But I will say that another thing we can look at is maybe we have our height here, and then some particle that could be here. And we could ask ourselves, is that one removed? And we could also consider if we had designed it so that the particle at the top was removed, then this one will land sooner. So we could imagine maybe this lands here if this one's all the way removed. Or we might say to ourselves, well, we're only getting some portion of them. And so at that speed, this one is ending up right here. And it turns out, because of simple geometry, this distance right here would simply be h minus hp. And that means that if that HP, or if the difference here, if HP was, let's say, 90% of H, we're actually removing 90% of the particles in this scenario. So it turns out to be a very convenient type of a deal to calculate or figure out how many particles are we actually going to remove. So let me remind us. We have a given Vs is the sedimentation velocity of a particular particle. Then we have the design velocity would be V naught. That's the velocity at which particles will be removed by this reactor according to its design, the physical design. And so if we have, we could consider it, if we have the design velocity is a larger number than our settling velocity, then not all of the particles will be removed. Vice versa, if the design velocity is smaller, definitely all of them are going to be removed, and we could even go further. We could remove smaller particles or slower particles. So imagine, again, the bowling ball if you have any confusion, right? Compare the bowling ball particle to a slower particle. If you design a swimming pool such that it should remove certain particles with some flow going through it, well, that's kind of overkill for a bowling ball. Bowling ball will hit the ground in a very short amount of time. So you could be flowing a lot of water through there and still settle out that bowling ball. So keep that in mind. When we make a comparison, we will compare between Vs and V naught. And we can take it a step further and get that ratio and figure out exactly how many are being removed. And it turns out that since that's directly proportional to the height, it's also directly proportional to the velocity. So if we want to know let's say what percent of particles are removed, the first thing we ought to do is check, well, is V naught smaller than Vs? Because it's 100% if so. So in this case, that's 100%. Watch out for the trick questions. Don't give me an answer that says 200% of particles are removed, because that's not possible. That's not a physical possibility. You can only get 100% of them, all right? You can't remove them twice. We're not stirring up the water. So look out for that. But if V naught is greater than Vs, meaning Vs is just too slow for this design, then we can compare. So first we'll check V naught versus Vs. That's not a good way to do it. The ratio here, then we can compare, as we'll show on the next slide. So if we have 100%, great. If not, then we will say, okay, well, are we at least getting 70%? Maybe that's good enough for our treatment, and then we'll capture the rest in the next step. That would be useful information to have. Okay, we'll get to the proportions in a moment. Just one more reiteration of how this will work if we have a given system where we have a radius here, area of the basin, like I said earlier, this is pi r squared. Whereas in this reactor, we'll have area of the basin as length times width. And we could consider the circular sedimentation basins as a cylinder. And if you put a radius on both sides, both the top and the bottom, and kind of have a center line, and then draw across any one radius, you'll find that is a nice rectangle. You could draw a wider circles. Maybe that's a little more accurate to scale. And it doesn't really matter where you draw it. You know, you could draw it this way and see that you're making a rectangle. Doesn't really matter where you're doing on that. And then you're watching the rectangle with a flow going out away from the radius, the center. So that's just elaborating, putting it here, hopefully clear for you one more time there. Okay, and do remember these values. I think you should be able to derive them on your own. I don't recall if I put them on the equation sheet, so go double check that. They're simple enough, I expect you to be able to figure it out if you needed to, right? The velocity, it's the flow rate divided by the area of the basin. I think I put it on your equation sheet, but double check. All right, so one clever thing we can do before I get to the percentages, so let me just double check that I have that. Yeah, okay. So one clever thing we could do to increase our settling rate is actually to increase our surface area. So if we imagine, looks like I left my little bit of a note from last time. If we imagine we have our sedimentation basin, let's say a rectangular one, one way we could increase the surface area is simply add shelves. And what this will do is, in a way, reduce the height that the particles have to fall as they're going through it. So one way to look at it is we're reducing the height the particles travel before they hit something where they stop. The other way to look at it is we're literally multiplying our area, right? Because each shelf has some area of that shelf. We can call it AB as well or something. So in this example, if each shelf has the same area as the ground, now we have 4 times the area, meaning when we write our design velocity is Q over AB, we now can settle particles that are 4 times as slow, this particular scenario. Now, as convenient as that sounds, it's not as convenient to harvest all the particles and keep them from getting back up and suspended into solution. So we might call this a high rate settler. In certain special scenarios they're used. It's not super common in drinking water treatment because, I think the risks are a little higher if we kick stuff back up, and it's a lot to manage mechanically to collect the particles and remove them without kicking them up and doing all that. So in some scenarios, these are quite useful. It's really smart to use physics that way, but not always. Yeah.
So like if you were trying to find that, you would multiply the area by 4, so like once each shelf.
Yeah, essentially, plus the ground. Right. We're not really going to do problems with this here, but I think what I wanted you to know is the concept carries over. And so maybe we'd do a problem where I say, okay, let's triple the area, and maybe I'll say it's a high rate settler. But just so you're seeing the connection between our criteria, right? I'm not going to have you calculate the geometry for shelves and angles and things like that. Just wanted you to know, just showing you a couple other features of sedimentation, what you can do with it, what's possible. Another possibility is to have what we call an upflow design. These are also not super common, and it's kind of an all or nothing system where you have water flowing upwards. Therefore, we have an upwards velocity vector just from the flow of the water, but we also have some downward velocity of our particles. And if you design this as like kind of a trapezoidal type of a system where you are increasing your area as you go higher, well, the upward velocity from the flow rate gets a little smaller as you go because you're going through more area. And so as you're collecting water over the top, that's your kind of effluent, so to speak, what's going to happen is you'll have some design velocity that your settling has to be equal to the velocity of water going over. So this would be your V naught, is that threshold of how quickly water is being pushed over the top. As long as you're under that, your particle should eventually settle. These are, I think, more commonly used in scenarios where particles, as they slow down up there, they tend to start meeting each other and forming aggregates and sinking faster. And so you'll almost have like a blanket type of a scenario where they're catching each other and then slowing down and sinking out. So it's kind of a strange type of system. Like I said, not used too often. I'm not going to ask you problems on this. Just an interesting thing. And in this particular scenario, we can use the same concept of V naught versus Vs, except that if V naught in this particular scenario is less than or equal to Vs, it's 100% removal, but if V naught is greater than Vs, we get 0 because the water is pushing them all over. So it's kind of an interesting scenario. Something like this might be able to be used for separating the size of particles, perhaps. If you have nice, discrete, different size particles, you could conceive of flowing it at a particular rate so that you're collecting all of one size and letting everything smaller or less dense or whatever, slower settling particles leave. So just kind of a curiosity there. Okay, so back to what I began talking about earlier. If we have a scenario where we're not removing all the particles, remember our design velocity is going from one corner to the next, right? This is our V naught. If that's not the case, well, how much are we getting given that we have some Vs that is clearly lower So Vs is smaller than V naught in this case. And smaller than means it's happening slower, means it's not as steep of a slope. So it turns out that if we want to know the percentage of particles removed, visibly we can say on here, if this is the 70% mark, then we're removing 70% of them. It's actually as easy as that. Now, mathematically speaking, that comes about because we have V naught is the height that they have to travel divided by the residence time, so distance over time for our velocity. And if we take a look at how many, the distance that a particle will travel given some Vs and compare it to this, then we'll be able to find what portion of particles actually make it out. So if V naught is equal to h over theta, we could say Vs is equal to the height of a given particle that it happens to travel given that amount of time. We can also remember that takes into all of the characteristics. So if we have some height, let me write this better. That should be the height of the particle, and this should be the height of the chamber. So we're designing it for the height of the chamber, and a given particle will be some arbitrary amount. So if we take a look at the speed at which a given particle travels, and we have some information about that, and we compare that to our V naught, the percentage removed will simply be, just as we see over here, the HP over H, or we can write it as Vs over V naught. We're going to multiply it by 100% to get it into percent. Okay, and again, that's because we have some Vs here where it is going, from some height and being removed in our time, and we just want to compare that with what we designed it for, or what the reactor's design velocity is. Okay, and I'm pretty sure I gave you this one on the equation sheet, so it's up to you to remember what those pieces mean and how you might use them. Remember also that because we have a V naught here, we can therefore design Q over AB and perhaps consider a few different flows or a few different basin areas, or even a few different particle velocities that we have to meet, and say, okay, given, and I'll post the next homework shortly, you might have one of these on there, given 3 different particle speeds, what basin area is required to make sure that they're all removed? Or perhaps, maybe we need 50% of the smallest particles removed and 80% of the largest particles removed. What's our size? It's actually not too hard of a problem. There's a few different pieces you have to go through with that. But as you see, these equations are not super complicated. So your task really is to make sure you're tracking with what we're referring to in each of these problems, like what physically is happening. Bless you. All right, is this making sense? Any questions?
So there's 2 separate settling velocities and then 1 critical velocity.
On this drawing?
Yeah, I'm just confused why there's two parallel line for settling velocity.
Good question. So we're wondering why we have 2 different VS's drawn on here with parallel lines. This is imagining I have a particle that starts here and some other particle that starts here. And so if we take the same size particle that's traveling the same speed as a terminal settling velocity and put it in different spots, you'll notice that anything that's placed given how this is drawn, at HP or lower, going at that speed, will be removed. But anything above there is not being removed because anything that does not hit the bottom before exiting is not removed. So everything here is not removed, and that's bad news. And everything faster than, or everything that started in the water lower than this point was removed because it didn't have to travel so far. So what I've shown here is I drew on here the diagonal, meaning the V naught, and then I just put two lines that are traveling at the same speed as an example of the particles that a portion of those particles are being removed. Thanks for the question. Okay, so let's give it a little practice. Here we have an example from our book, silt remover in a clarifier. So we have a drinking water treatment plant uses a circular sedimentation basin to treat 3 million gallons per day of river water. And it explains MGD and gives us a conversion so we can get that into cubic meters per second. So after a storm occurs upstream, the river often carries 0.01 millimeter silt particles with an average density of 2.2 grams per centimeter cubed. And the silt must be removed before the water can be used. The plant's clarifier is 3.5 meters deep and 21 meters in diameter. The water is 15 Celsius, and the questions are A, what is the hydraulic detention time of the clarifier? And B, will the clarifier remove all of the silt particles from the river water? Okay, so we've got 15 degrees water. That corresponds to a density here, 999.1 kilograms per cubic meter of water, and a dynamic viscosity here. That is 1.139 times 10 to the minus third kilograms per meter per second. So don't forget the unit there. Okay, so give this a few minutes. Definitely you should be able to solve A. That is, I absolutely expect that of you. I'll solve it with you, but make sure that if you are getting hung up on that, let's figure that out. And I want you to start on B. You've learned enough to get it, but there's some unit conversions and things like that, so it might take a few minutes and there's places you could get lost. So give it a try and work towards making sure that you could do this if I gave you it as an exam today. You're welcome to work together if you'd like to. Yep. No, not in a day. That's how many minutes are in a day. 3,600 minutes in a day. Or no, I'm sorry. Seconds. That's what I was thinking. Yeah, 86,400 seconds in a day. Yeah. All right, so I went ahead and solved part A for you, so double check on that. See a few confused faces. It's possible I did something wrong, but these numbers look correct, and I did it in Excel, and that's always a better thing for me. So just real quickly, I'll explain that, and then I'll get you started on part B, and then I'll give you another couple minutes on that. So we've got a question about the retention time. So V over Q is what we're looking for, so we need our volume. We're going to get that from the volume of a cylinder because we've got a circular clarifier. It's going to be essentially a cylinder. It's got a height of 3.5 meters. Always draw your thing, by the way. Whatever we're doing, draw it first, always helps. So we've got this cylinder type reactor or sedimentation chamber, 3.5 meters high, 21 meters in diameter. I'm going to take pi r squared as the area, so half of 21 is 10.5 meters. I'm going to square that, multiply that by pi. That's going to be our area. Calculated that to be 346 square meters. Multiply that by the 3.5 to get the volume. It should be about 1212 cubic meters. Okay, then we're going to take the flow rate, which was given at 3 million gallons per day. Rather than trouble myself with how many seconds are in a day, I just used their conversion here because it was given in the problem. Said 1 MGD is 0.0438 cubic meters per second. So I just went straight over to seconds and cubic meters by saying we've got 3 of those, so multiply that 0.0438 by 3, and we've got it. So the flow rate I calculated was 0.1314 cubic meters per second. That'll give us a hydraulic residence time then of 9,226 seconds, or about 153, 54 minutes. You could put that in hours or days if you wanted to. I just left it in minutes for now. That would be part A. So part B then, we want to know, will the clarifier remove all the silt particles from the river water? And by the way, any questions or issues on the part A? Does that make sense? Just some unit conversions primarily and a little bit of geometry, right? Okay, so part B, we want to know, will the clarifier remove all the particles? Essentially, we need to compare, is V naught greater than, less than, or equal to Vs, right? And if we, like, I already forgot the slides that we did this. Is it less than or greater than? So I have to stop and think about it. Just like you probably have to stop and think about it. Okay, if our design is one speed and the other is slower, then we're not removing everything, okay, because it's not going to reach the bottom. So if the design is smaller than Vs, then not all removed. And really, this is a question, is this smaller, right? Or excuse me, if the actual settling is happening slower. Did I get that backwards? So basically, I want to know which one's which, and then at the end, I'll think about it again, right? So if the particle settling velocity is slower, then we're not going to remove everything. Okay, so I corrected it. Okay, so then we need to solve for both. And remember that one of these is based on the particle characteristics and what's happening with the water, just like the skydiver. The other is based on the flow dynamics of our chamber. Okay, that's always the distinction. Sometimes we'll relate them on purpose to say we're going to design for this particular particle, set that equal to such and such, but inherently this is the setup, right? So we have Q over AB, and then our equation here would be this guy. All right, how are you feeling on it? Sounds like units. A few of you are like a little troubled by the units, maybe, and then somewhat okay otherwise. Does the process itself make sense? Where we're going with this? Let's see. Did you kind of see that from the beginning, or like as we started going through it, you're seeing a little more clearly like how to get a solution? Is that feeling all right? Okay, so I went ahead and began this. So I gave you these two equations, right? So Q over AB for the design velocity. And we already solved for those problems, so I went ahead and wrote these up here. That would be the Q that we calculated. It's convenient to have it in meters per second. So we use that cubic meters per second, 0.1314, divide by our area that we calculated, the pi r squared. That should give us a value of 3.79 times 10 to the minus fourth meters per second. These are very small particles. They settle out pretty slowly. They should not be, like, if you think of a bowling ball going maybe a meter in a second or more, that's not really the settling velocity we're looking at, right? It's going to be a low number, like a 10 to the minus 3, 4, 5 type of number. So if you're in that ballpark, you should be feeling pretty good. Now the other side, we have the S. Here's the sedimentation calculation. We need the settling due to gravity. That should be 9.81 meters per second squared. The rho of the particle, that's maybe giving some trouble here. The rho minus the rho of the water, that's on our lookup table, so that should be 999.1. Diameter of the particle, that's another piece that could give some trouble with the units. This was 0.001 millimeters. Another way to write this would be 0.01 times 10 to the minus 3 meters. Or we could also write it, if you wanted to be fancy, 10 micrometers. So whichever way you take it, you're going to end up with some number that is 10 to the minus 5 meters. Okay, so that's our diameter of the particle that we're going to need. And we want to put everything in meters because all the pieces will go nicely if they're all in meters. Technically, you could put them all into centimeters. I don't recommend doing that. So then we have the problem of the rho being 2.2 grams per centimeter cubed, which is a pretty common way to measure the density of something, how many grams in some volume. The cheat code is that it's typically the same order of magnitude as the water. It's typically not far from it and higher than the amount of water. So the easy thing in my brain is to say, okay, it should be 2,200. Now, the thorough way, so that's maybe a good way to double check your calculations to say, hey, is this going to be actually heavier than water for a sedimentation problem? Or more dense than water, rather? Good? Yeah, great. It shouldn't be 220. So that's much lighter. It's never going to settle. It's going to float. Is it 2 million times the density of water? That's probably wrong also. Okay. So the proper way to do the conversion would be to multiply the grams by 1 kilogram per 1,000 gram. That'll get us to kilograms. And then on the bottom, we need to convert, there's 1 meter per every 100 centimeters, but we need to cube that 100 with the conversion, like I explained before. So once you do that, that should give you 2,200 kilograms per cubic meter of these particles. Of course, we're never going to have a cubic meter of these particles typically, but that would be the density if we did. So with that, we can then put in our numbers. I'll just go ahead and show you. I kind of have all this laid out here, and our settling velocity then should be 5.75 times 10 to the minus fifth. So Vs, when we put all those numbers in, should be that many cubic meters per second, and therefore Vs is smaller than V naught, meaning not all removed. Okay, so ran out of time, so we'll cover coagulation next time, looking into how we might fix this problem. Okay, we'll see you next week.